Hi everyone. In this video we will be talking about polynomial and synthetic division. So we have been looking at rational expressions, how to add them, how to multiply, divide them, the concept of a lowest common denominator, combining them, factoring, cancelling out what's possible. So an extension to that is, if you have division of two polynomials, is there a process that is parallel to the division of numbers? So since we are trying to draw a parallel with division of numbers, that's a natural place to start. Now when we divide two numbers, right, this results in, it usually gives us two numbers, right? It gives us something called a quotient and it gives us something called a remainder. Now how this long division works is, we put the numerator in here, the denominator in here, and then we look at how many times does 7 go into 14, and that is 2 times. And we write down the result of 7 times 2, which is 14, and we subtract. There's nothing left here, and then we bring down the next number, 7, and then we see that 7 goes into 7 one time, and 7 times 1 is 7, and we stop. So we stop when there is 0, which is less than 7. So we stop if this number is less than 7. So in this case, we say that the quotient is 21 and the remainder is 0. Let's repeat the process for the second one here, slightly longer. 7, 7, 3, 6, 7, and 11. So since 7 is smaller than 11, I take 2 digits. So 7, 7, and that goes into 11 7 times to give me 77. Subtracting gives me 0, right? That's 0. Now I bring down the first number, 3, but that's not enough. So I have to bring down the second number. When I do that, I add a 0 here, and then 11 goes into this 3 times to get 3, and then I bring down the next number and it goes 3 times again. Now 4, that's less than 11, so we can stop. So in this case, the quotient is 7033 and the remainder is 4. Now recall that remainder 0 means that 147 is divisible by 7, or that 7 is a factor of 147. So this particular language of divisibility and of being a factor, it carries forward even when we talk about polynomials. Now there's a certain relationship between the divisor, dividend, quotient, and the remainder. For example, 147 can now be written as 21 times 7 plus 0. Right? So this here is the quotient, and this here is the remainder. Okay, so you can always write down the numerator as product of the quotient, denominator, plus the remainder. In the same way, the second one can be written as quotient times what we were dividing by, divisor, plus the remainder should equal the number that we started with, which is 77,367. Okay, once again, labeling here, that was the quotient and this is the remainder. So this particular way of expressing the division result as quotient times something plus remainder is going to follow in the case of polynomial division as well. And that is why it sort of helps to look at it first in terms of numbers. So our goal here is to progressively build up in order to be able to divide two polynomials. Now we know that what two polynomials what are they made up of? They're made up of single terms that contain numbers and variable with some power, right? Something like they may have 27x squared or 9x cubed. So we know how to work with numbers already based on this division. The next thing that we need to look at is the exponent law for division of monomials. So this is, for example, if you're working with numbers, if you have 2 cubed divided by 2 squared, right? What does that mean? That really means there are 3 copies of 2 in the numerator and 2 copies of 2 in the denominator, so that 2 of these cancel and you are left with 1 copy of 2. This can also be formulated directly as saying this is 2 to the power 3 minus 2, which is 2 to the power 1, which is 2. Okay, so basically what is this saying? This is saying that if I have a number x to the power m divided by x to the power n, then it simply becomes x to the m minus n. You've already seen this in some factoring examples, right? For example, x cubed over x is x squared, or x to the 4 over x is x cubed, and so on. So the first thing we saw is how the numbers divide. Second thing we saw is how just the exponents of the variable, like x to the power something over x to the power some other thing, how does that division work? Which means we can combine them. So for example, if I have to find 25x to the 12 divided by 5x to the 4, then that is 25x to the 12, 5x to the 4. Now this one I apply the result for numbers, and in this one I apply the result for the variable. 25 over 5 is 5, and x to the 12 over x to the 4 is x to the 12 minus 4, so that is x to the 8. Okay, so that is the first case where we combine the numbers and the variable. Now let's go one step further. Now let's say you have a whole expression dividing 5x. Right, so in this case what we are going to do, we're going to break this down into 2 steps over 5x. Now because the denominator only contains one term, we can distribute it to each term. So this can be written as 15x cubed over 5x minus 5x squared over 5x plus x over 5x plus 5 over 5x. And then we notice that 5, 3, x squared, 5x gets rid of the 2, x and x cancel, 5 and 5 cancel. So what we are left with is 3x squared minus x plus 1/5 plus 1 over x. One more example. There's x and y mixed up here, right? So again, we do the same thing. We write this as a fraction with a numerator and a denominator. Thereafter, we distribute the fractions as 8x to the 4 y to the 5 over 4x cubed y squared minus 10x to the 4 y cubed over 4x cubed y squared plus 12x squared y cubed over 4x cubed y squared. And then we cancel what we can. 4 goes into 8 2 times. X to the 4 over x to the 3 gives me 1x. Y to the 5 over y squared gives me y cubed. 4, 2, 5, x cubed x, y squared y, 4 goes into 12, 3, x squared y, y. So we end up with 2xy cubed minus 5xy over 2 plus 3y over x. So these are just warm-up examples covering the very basic case of dividing numbers, dividing just the variables, dividing by a monomial. Okay, that's the end of this video. Next video we're gonna go a step further, and then we're gonna look at how to do the long division when we have more than one term. Okay, that's it for this video. Thank you.